Welcome back, everybody. More convergence tests. All right, so last video we showed a few. We maybe did a proof or an example, but here we're just going to list off a whole bunch of them. So our very first one is going to be the comparison test. So this is used when you want to show that a particular sequence subverges, but you know that some other sequence subverges, but you know there's something connecting the two. So here we're going to assume we have two sequences A and B, which are eventually non-negative. Okay, it's okay if there's zero, that's fine, but we don't want them to ever be negative, at least in the tail. Okay. The other thing we're going to want is that eventually we want that the nth term of A is less than or equal to the nth term of B, which I would shorten this up. I mean, it doesn't really look shortened, right? So this is for all n greater than or equal to n for some positive integer n. Okay, so there's some tail of both A and B such that when you go to those tails, the terms of A are less than or equal to the terms of B, or I would just say eventually A dot is less than or equal to B dot. That would be my shorthand way of writing this. Okay, so that's just the hypotheses. So the actual conclusion of the comparison test is if you know that the larger sequence, okay, so the B, if it subverges, then the smaller sequence also has to subverge. So if B subverges, then A subverges. Okay, so remember this is meaning that the series corresponding to B, if it converges, then the smaller series, the one corresponding to A, also converges. All right, the second goes the other way around. If you know that the smaller sequence disubverges, so if A disubverges, then the bigger sequence is also going to have to disubverge. Okay, so this is pretty useful to compare things where you know one is bigger than another, right? So for example, we might look at 1 over n, and we know that 1 over n is going to disubverge. So if I can find some sequence which term by term is going to be greater than 1 over n, then I know it will also disubverge. So I can make things greater than 1 over n by making, well, the denominator smaller. So for example, I know 1 over n is greater than 1 over, I don't know, how about n minus 4? Okay, so 1 over n minus 4. Now, of course, if I'm going to start at 1, then I'm going to have this problem when I get to n equals 4. So I probably want to start the sequence when n is at least 5. But that's fine. We don't worry about that. All we care about is eventually anyway. But because we know that 1 over n disubverges, and I wrote this the opposite way. We know 1 over n minus 4 term by term is greater than 1 over n. We know that this is going to disubverge without having to prove that this sum sequence diverges using the definition of divergence of a sequence. All right, we can just compare it right off the bat. Okay, to do the next theorem, we're going to need a definition. So the next theorem is going to be the absolute convergence test. So I have to tell you what absolute convergence means. So a sequence A, we're going to say that it subverges absolutely, or absolutely subverges, if the sequence you get by taking the absolute value of every term in the sequence A, if that sequence subverges. Now, it's also possible that A subverges, but that the absolute value sequence disubverges. Okay, so we give a special name to that. So if the absolute value sequence disumverges, and the original sequence A subverges, then we say that A subverges conditionally, which I don't love. Okay, I'm going to capitalize this here, but I don't love this phrasing, conditionally. It makes it sound like, oh, there's some condition that would make A subverge. And that condition is that it's itself. Don't take the absolute value. Okay, so let's write down then the absolute convergence test. Which is simply going to say that if A subverges absolutely, then it just it subverges. So then A subverges, which you might say, well, what good is that? The good is sometimes it's easier to take the absolute value and not have to worry about positives and negatives. Or you might be able to couple some things together. If I take the absolute value, then my terms are definitely non-negative, in which case now I can use the comparison test. So I might be able to pass from the original sequence to the absolute value sequence to some comparison sequence. Okay, and that could be very handy. All right, let's actually give a proof of this. Right, not too bad. So we're going to assume, right, that the sequence subverges absolutely. And by the Cauchy criterion for series, then we know that each of the, well, let's write this down here before we get too far into it. So by the Cauchy criterion for series, we know that the sum sequence for A absolute value, right? So we know it subverges absolutely. So if I look at the absolute value of A and I take that sum sequence, then that is going to be a Cauchy sequence. Okay? So the sum sequence for the absolute value is a Cauchy sequence. Okay, so if we know that a sequence subverges, then we know that the sum sequence is a Cauchy sequence. Okay, what did it mean for a sequence to be a Cauchy sequence? It meant that if you have any zero coin, then it will contain a tail. And when we looked at what this meant in the situation of a tail of, by the way, of the 2D difference, right? And when we looked at these sum sequences, then we saw that meant you would just look at sort of these partial sums, things that looked like absolute value now of a m plus 1, and so forth, absolute value of a n. That's what things in the 2D difference, right, looked like. So when we were looking at the 2D difference, okay, this is what things looked like. So we need that if we go out far enough, expressions of this form will lie in a zero coin that somebody has chosen. Okay, so let's choose some zero coin, right? So we'll let epsilon be greater than 0. This is going to give us the zero coin negative epsilon to epsilon. So we know there exists some tail, so we get some distance out in the sequence. So this is a positive integer n of epsilon, such that, okay, well, let's see. Let's say I take some n, which is at least m, which is at least this n of epsilon. All right, so I take two terms past the tail, then this guy we get here, a m plus 1, absolute value plus dot dot dot, plus a n, is in the zero coin of radius epsilon. Okay, but if I put this together, all right, if I put this together so that there's no absolute values, oops, except for the entire, like one absolute value, then this is doing the triangle inequality, right, from right to left. So this would be less than or equal to the sum of the absolute values of these terms. And we already know that when I add up all these things, right, this is going to be less than epsilon. In fact, we say it's between negative epsilon and epsilon, but these are all non-negative, right? So we don't have to worry about being in the negative side of this interval. So this sum will certainly be less than epsilon, and it's greater than or equal to the absolute value of this sum. But if the absolute value of this sum is less than epsilon, then that implies we'll drop the absolute value, that this has to be in the zero coin of radius epsilon. Well, that tells us that if we take these types of terms, right, notice there's now no absolute value. This implies now, right, we're looking at things in the 2D difference, not of the sum sequence for absolute value of A, but of the sum sequence just for A. All right, so we're looking at 2D differences, right, sum sequence for A. And so that's telling you that this sum sequence just for A is a Cauchy sequence. Because we've now shown, right, for the exact same tail, right, every term in the 2D difference of the sum sequence is in the zero coin of radius epsilon. And now we just use the Cauchy criterion for series in reverse. We know we have a Cauchy sequence, and so I'll abbreviate by the Cauchy criterion. Then we know that A subverges. Okay, so we know that the sum sequence converges, so A subverges. Okay, and that's the proof. All right, so this Cauchy criterion is actually quite nice for proving these things in a pretty straightforward way. All right, what is the next one? So next one, well, we're going to need another definition. And why do we need a definition? Well, it's going to be for the alternating series test, so we need to define an alternating series. So it's actually going to come from an alternating sequence. So a sequence is called alternating. Well, what's alternating? It's going to be the sign. Okay, so if it is of the form, we're going to write negative 1 to the n times an, where an is eventually non-negative or non-positive. So that's okay if they're always negative, that could be, or you throw in some zeros, or if they're all positive, right? What you don't want is for them to be jumping back and forth between positive and negative and messing up with this alternator here, which, by the way, this piece right here we're going to call the alternator. Now, because of this flexibility here, where we can have eventually non-negative or eventually non-positive, I can also write down an alternator that has an n plus 1. So in this case, right, I could view this as being in the original form by just saying, oh, well, okay, this is negative 1 to the n times negative an. So if an was eventually non-negative, then negative an will be eventually non-positive. So I can fit into either one of those, and I always take it back to this. So this would be an example of another alternator. And if I need to distinguish out loud, I might call this an n alternator and this an n plus 1 alternator. What you don't want to get into is something like negative 1 to the 2n an, and you say, hey, yeah, look, I have a 2n alternator. But this is problematic because negative 1 to the 2n is always equal to 1. Right? Does not matter what the n is, because you could view this as taking negative 1 and squaring it and then raising it to the nth power. And negative 1 squared is 1, and 1 to the n is 1. So this is not an alternator. Okay, so you have to be careful. You really need to have some function here, which is oscillating between odd and even. Okay, you can't have it always be even. All right, so that's an alternating sequence. Now, if I take an alternating sequence and then write down the corresponding sum sequence or the corresponding series, then we'll call it an alternating sum sequence or an alternating series. So the corresponding, and I'll just mention it for sequences here, but or a series rather, the corresponding series is called an alternating series. Okay, so now we can get to the alternating series test. So let's say that we have an eventually decreasing sequence of eventually non-negative numbers. And you can imagine what would happen if I have eventually non-positive numbers, okay? But we can just prove that as a corollary of this. So we're going to assume that A dot is eventually decreasing and eventually we're going to say non-negative. Okay. If we want to make this eventually non-positive, then we'd want this to be eventually increasing. Okay, so we also want A dot to converge to 0. Okay, of course, if it's not converging to 0, then by the non-vanishing sequence test, we know that A disumverges. Okay, so the claim then is that if I look at, and I'm going to use, instead of an n up here, I'll just use the dot on the -1. So I'm looking now at an alternating. Okay, we're going to look at an alternating sequence, right? So the alternating sequence. Notice the dot allows me to maybe have some different exponents up there other than just n. I can use different alternators. The alternating sequence, -1 to the dot, A dot, which is just going to be -1 to the, well, right, this could be to the n, A sub n. Okay, we want to line these up, okay? Subverges. Okay, so as an easy example and an important example, if I look at the series starting at 1, where I take an alternator and then I multiply it by 1 over n. So this is called the alternating harmonic series, because it's the harmonic series, right, coming from 1 over n, but it has an alternator. Okay, well, we check. If I ignore the alternator, right, ignore the summation, I'm just looking at this underlying sequence 1 over n. Okay, so my A dot here is just 1 over n. This is eventually decreasing. In fact, for n at least 1, it's always decreasing. And it's eventually non-negative. Heck, it's always positive. And it converges to 0. Right? 1 over n we know goes to 0. Without any extra information, we know automatically that when I take the alternating harmonic series that this converges. Okay, or if you prefer, -1 to the n times 1 over n subverges. Now, that's the good news. The bad news is that unlike the geometric series test, which tells us precisely what the series converges to, here we don't know, right? We're going to have to make some extra argument in order to figure out what it converges to. But if all we care about is that it converges, that could be enough. Another beauty of this is that if we take the absolute value of each term and we check for convergence or subvergence, and we find out, oh no, it actually disumverges. So it doesn't subverge absolutely. It still might subverge conditionally. And the alternating series test actually gives us a way of potentially checking that. Now the last test we're going to write down here, actually this gets back to absolute convergence and why we really care about absolute convergence, which is, or absolute subvergence, which is that it actually tells us that we can rearrange the terms in our sequence without affecting the value of the series. So let's make this precise here. So we'll write down a definition. What do I mean by a rearrangement? So let's let A be a sequence. Okay, so over here we might have, right, A equals A1, A2, A3, A4, etc. And the idea is I want to just change the order in the sequence, and maybe in just some random looking way, right? So maybe I write down some A dot prime, which is going to be A3, A10, A14, A1, A2, A5. You'll notice I'm not repeating any of them, all right? And hopefully I'm going to get everything eventually. So what I've done is I've permuted all of the positive integers essentially, which means I have a bijection of the positive integers to themselves. So A is going to be some sequence, and we're going to let F be a bijection from the positive integers to itself. All right, so now I'm going to set, well, let's call it, I don't know, how about B for right now, right? We're going to define a new sequence B, which is going to be simply the sequence I get when I compose A with F. Okay, so first I permute the numbers, and then I take this sequence A. And so this would be A F of dot. Okay, so if I put in, F of 4, that would be the very, or F of 1, that would be the very first thing, right? So I would have A F of 1, A F of 2, A F of 3. Okay, so up here you can see F of 1 is 3, F of 2 is 10, F of 3 is 14, F of 4 is 1, and etc. Okay, so there's a new sequence B. Okay, the sequence B is called a rearrangement of A. Okay. Right. Now, what if I know that A subverges to some limit L? So if A subverges to L, well, I now have this new sequence B, and I could ask, does it subverge? And if it does subverge, what does it subverge to? And it turns out that if A just subverges to L, that doesn't really tell me enough to say anything about B. But if I go back here and add in that A subverges absolutely to L, then it does not matter how I rearrange it, B also subverges to L. In fact, it'll subverge absolutely. Okay, so we're not going to prove that right now. Okay, this is actually, I should call this a theorem here. We're going to prove this in the next pass through the course. Okay, there are lots and lots of other convergence tests. I could make probably another 2 or 3 videos of the same length, just based on the ones that you might see in Calculus 2, or maybe even going a little bit further. But this is going to be good enough for now. Probably go back, look at your Calc 2 book, and see some of the other tests just to get them refreshed in your mind. All right, in the next video, we're going to jump into some topology, the topology, though, of the real numbers. So we'll learn about open sets and closed sets, and then we'll move on to compact sets, all sorts of good stuff coming. All right, we will see you then.